Hello everyone, welcome to the Spectral Geometry in the Cloud seminar. Today we have Gibara who will speak about Dirichlet-to-Neumann map for the p-Laplacian on a metric measure space. Ryan, the floor is yours.
Thank you very much. And thank you to the Spectral Geometry in the Clouds group for inviting me. I have to start this talk by saying that I'm not a spectral geometer, and I have absolutely no experience working with these things. So what happened was that my collaborator Nageswari Shanmugalingam and I at University of Cincinnati deal with boundary value problems in the setting of a metric measure space. And we had always kind of, at least I'd always been surrounded by people talking about the Steklov problem and Dirichlet-to-Neumann maps and things, but I never quite understood them. So we decided to do a little project starting thinking about these things in a more general setting. So I'm very welcome and I'm open to comments, criticisms, things that people want to let me know because I don't know much about this. So let's start. I have to give you a bit of a crash course in metric measure spaces. So what do I mean by a metric measure space? I have a metric space omega d, and I have a Borel measure on omega that gives finite but positive measure to balls of positive and finite radius. So this is a general metric. This, of course, is obscenely abstract, right? This can mean can be almost anything. We have to add some conditions to be able to do analysis in this setting. The first one is that I want my measure to be doubling, which tells me that I have comparability between the measure of a ball and the measure of the concentric ball with twice the radius. And once you have doubling, you can do a lot of 0th order analysis. It kind of carries through, but we're interested in higher order analysis. And I can at least go to 1st order in this level of generality. So the second condition I need is I want my space to support a Poincar inequality. So I have some p strictly between 1 and infinity. By a Poincar inequality, I mean that I can control mean oscillations of functions on balls by radius times an average of the derivative. But I don't have a derivative in a metric measure space, so I'm stating it for locally Lipschitz functions, where on the right-hand side of the Poincar inequality, I can put the local Lipschitz constant. I know if you're in the Euclidean world or if you're used to more concrete settings, the Poincar inequality is a result that one proves. But in this level of generality, it's an assumption that you place on the space. You say, I have a space that does support such an inequality. Can I use it? And it immediately implies a lot of geometric conditions on your space. For instance, immediately omega must be connected for this to hold. And in fact, in this setting, I'm going to have nice geometry of curves in my space. I'll talk more about that later on. So now that I have a metric measure space, let's talk about.
Yes. Sorry, Ryan, I have a question on this. So you say that you have a Poincar inequality, yes, then you can deduce plenty of nice things. Are there things that will immediately imply that you do have a Poincar inequality?
That's a much more difficult direction. Mm-hmm. So what I'm doing is I'm saying I don't want to have a situation where I don't have enough curves. I don't have enough geometry. So I'm placing this as my standing assumption. Going the other way is much more difficult, right? Saying in some general setting, if you have Poincar is the harder one. I'm assuming I have it.
Yeah.
This removes a lot of pathological examples in which case we don't want to do 1st order analysis in those settings.
Yeah. All right, thanks.
No problem. I also didn't say this, but please feel free to interrupt me at any point if I'm not clear. Otherwise, I'll just keep going. So now that I have my setting, I want to talk about Sobolev functions. But I'm in a metric measure space, so I don't have a notion of derivative, right? And this is where the first thing you have to do is decide how to define Sobolev functions in this setting. There is no unique way to do it. It turns out that there are multiple different kinds of Sobolev spaces. But in very nice situations, they all coincide because you would expect them to then all coincide with the standard one if you took your space to be Rn with Lebesgue measure and Euclidean distance, right? But you have to choose how you want to generalize things. And I want to use what are called upper gradients. So if I have a function u on my metric measure space, I have an upper gradient g if this inequality holds, which of course should be reminiscent of the fundamental theorem of calculus, right? If U were a smooth function, then without the absolute values, I would have equality here, and G would be the gradient of U. However, we're looking at a setting where I don't have a gradient of U, and for general Sobolev functions, they're not going to be smooth. So even what does it mean to talk about U at X and U at Y? But once I put absolute values there, this is the inequality that I can easily generalize. So my G is not so much the gradient of U as it is the modulus of the gradient of U, right? Because that's what would be there in the fundamental theorem of calculus. If, however, it doesn't hold for every curve, it might hold for most curves, then what we call it is a p-weak upper gradient. So on the collection of rectifiable, non-constant, compact curves, you can define an outer measure that's called the modulus of the family of curves, and that lets you throw away some of them without losing too much. So if we're allowed to throw away some curves, we have a p-weak upper gradient. And indeed, if you were in Rn, then the modulus of the gradient of a Sobolev function would be its p-weak upper gradient almost everywhere. Even more so, if I happen to have a function and it has a p-weak upper gradient that is in LP, then I will have a minimal p-weak upper gradient, okay? So this is kind of like up to sets of measure 0, the unique notion for a modulus of a gradient that I can use. So this is one way to define Sobolev spaces. So let's see what the definitions are. I can talk about D1P, the Dirichlet-Sobolev space. This is the collection of measurable functions that have an LP p-weak upper gradient. And then by the semi-norm, I mean the LP norm of this p-weak upper gradient. This is analogous to a homogeneous Sobolev space, right? I can also talk about what I call the homogeneous Newton-Sobolev space, HN1P. This is if I consider D1P modulo addition of constants. So we're going to be talking about Neumann problems. Then everything is kind of up to a constant. So I have to have two kinds of notions of homogeneity. And then I have the inhomogeneous Newton-Sobolev space N1P. That is the D1P functions that have that are themselves in LP. And then this is kind of like the Sobolev space, right? The norm is the LP norm of the function plus the LP norm of what plays the role of the gradient. This is one way of generalizing Sobolev spaces in this abstract setting. It's not the only way. It is in some sense the way that takes into account the most geometry of the space. So for instance, if I had omega and omega had no rectifiable curves, then N1P would actually be all of LP, because the only kind of upper gradient I could take would just be, I wouldn't have one, or I could just take the constant infinity as an upper gradient. So I need to have some kind of rich geometry in my space to have this be a non-trivial Sobolev space. Whereas if you pick other notions of Sobolev spaces, they may work in kind of uglier fractal settings that don't have rectifiable curve. So now we know what I mean by Sobolev function in an abstract metric measure space. And I have to talk about one more kind of technicality, which is the notion of a Cheeger gradient. So remember how I said there are many ways of doing Sobolev in this setting. When your space is doubling, right, that was one of the kind of important conditions, and I have a Poincar inequality. Cheeger showed in a paper in 1999 that in fact you have what's called a Cheeger differential structure, which means that you, in this special setting, you see I've added lots of conditions. In this special setting, there is going to be some n so that I can identify for each D1P function an actual vector gradient in R to the capital N. So this kind of capital N is kind of like a Cheeger dimension for my space. And this is much, much stronger than having an upper gradient. Upper gradients don't need doubling, don't need Poincar. I can define them as long as I have enough geometry. But this kind of notion of an actual vector that represents the gradient needs much more. And this is why you need doubling and Poincar. So we can have gradients. In fact, this Cheeger differential structure really is the existence of an inner product with respect to which you can define this vector that behaves like a gradient, and then a norm. And so what you can do is you can kind of consolidate these two pictures. You can consolidate this upper gradient idea with the Stiger gradient idea by selecting your inner product in such a way that the norm of this vector gradient u is equivalent to your p-weak your minimal p-weak upper gradient. So you can define d1p, n1p, hn1p instead of as LP norms of the GU as LP norms of the gradient of u. And you're going to see why we need this kind of much stronger kind of notion of Sobolev derivative. And it's stronger, but it's also more difficult to understand, right? I'm not giving you the formal definition of anything here because it would take pages and pages of slides just to get this definition right. And it's much more strict and much more complicated, as opposed to the kind of the geometrical kind of notion of upper gradients. So you can kind of have both pictures in your head at the same time.
Ryan,
Yes.
I have a question.
Yes.
In the case where say you have omega here, your omega is in the classical case would be a domain in Rn, or could be a manifold?
Could be a manifold.
What I'm trying to understand is, if it's a manifold with a distance and the usual Riemannian measure, where would the gradient live? Because usually it's a tangent vector field, but now you're saying it would be in Rn, not like in a section of some bundle, so I'm not sure. What is it in the classical case of a manifold?
So your n here would be the dimension of your bundle.
Like for a surface, it would be 2 because it's two-dimensional.
Yeah.
Okay. But if you take just the gradient of some function on a sphere, for instance, usually the vector is in a bundle. It's not in Rn. That's why I'm confused. Yeah,
but you can identify. So you can think of it maybe instead of in terms of gradients, you could think about it in terms of like differential forms, right? And so this is not going to give you exactly the same thing that you get in a Riemannian surface, because the Sobolev space is not exactly the same as this. In particular, you can't really change your function up to sets of measure 0, but it's going to be up to constants equivalent in some sense, right? I'm not really very Riemannian manifold oriented, so I don't really know how to answer your question so well. I'm sorry.
Thank you.
But if you were in Rn, of course, this would be just the modulus of the gradient would be the GU.
Okay, thank you.
Yeah.
Sorry, can I ask another question?
Of course.
I think on the previous slide, or maybe 2 slides ago, you had a line integral of a this thing. So can you define line integral before you have an inner product?
Yeah, of course. Just by parametrizing. So if G is Borel, then you can take the integral just by looking at like a line integral, like sums, right? I don't have an iPad or anything, but so you don't need an inner product to define an integral. You just need to have parameterization of your curve, right? So you're going to be looking at G of gamma of S times the derivative of gamma, and gamma is a curve on Rn. So you can just take the metric derivative of your gamma.
Oh, it's in Rn. I see.
So the curve, right, is going to be a curve on your omega, but the values are in Rn. So you can do a derivative in the same way that you do a classical derivative. It's called a metric derivative. So in fact, you can always parameterize by arc length, in which case it's going to be a metric derivative is going to be 1. And so this integral over gamma of G is actually the integral from 0 to the length of G evaluated at gamma of S. And as long as gamma is a Borel function, then that's going to be well defined.
I see. Okay.
Yeah.
Thank you.
Yeah. But please, if you have trouble consolidating the Riemannian case with this stuff, this is great, because I don't know much about that world. I come from Euclidean and I jumped to metric measure spaces. So these are all very good things.
Thank you.
Now that I have some different notions of Sobolev, let's talk about boundaries. So if I have a non-complete metric space What I mean by its boundary is actually the difference between the completion of the space and the space itself. So this is my notion of a boundary. So if I'm going to be talking about boundary value problems, I have to have a notion of boundary. And on this boundary, I can put another measure, right? So if we think about the smooth case, we're thinking about omega being a smooth domain. And then on the boundary, you're going to have the n-1 dimensional Hausdorff measure. But I'm in a more general setting, so I can have a Borel regular measure on my boundary. I want to talk about it having a certain codimension, right? So there is no notion of dimension or anything, right? These are kind of abstract, potentially kind of infinite dimensional spaces. They are kind of finite dimensional once you add a doubling condition. But if I have a Borel regular measure on my boundary, I can talk about being theta codimensional if the new measure of balls centered on the boundary is comparable to the mu measure inside my domain divided by r to the power of theta. So in the smooth case, let's say if I have a smooth domain omega, and I want my nu to be the n-1 dimensional Hausdorff measure, my theta would be 1. Because my mu would be Lebesgue, which is n-dimensional, divided by r is comparable to my n-1 dimensional Hausdorff measure of a ball. So this is how I can talk about the codimension of a boundary. So now I want to talk about what functions am I going to be looking on the boundary. I'm going to be looking at Besov functions. So by B dot, I mean the collection of all measurable functions that have finite Besov energy. The Besov energy is this double integral of you're looking at the difference of f of x minus f of y raised to the power of p, but now you're dividing by one piece that's just the distance between the 2 points, another piece that's the new measure of the ball centered at 1 that's going to be large enough to contain the other. If we were in the standard case, right, let's say Euclidean case, then the measure of the ball would be like the dimension or the radius, the distance between x and y to the power of the dimension. And this 1 minus theta over p times p is what we usually call SP. So if we combine this denominator, this is really saying I'm dividing by the distance between 2 points to the power of the dimension plus s times p. So this is actually just the Galliardo seminorm for the fractional Sobolev space WSP in a domain in Rn. But this is the kind of one of the potential versions at this level of generality, which is called the Besov space. So this is my B dot. I can now talk about the homogeneous Besov space as being B dot modulo the addition of constants, right? Because again, we're going to be thinking about Neumann problems. And then I can talk about the inhomogeneous Besov space, analogously to how I had an inhomogeneous Newton-Sobolev space, as being the B dot functions that are also in LP. And now the norm is going to be LP plus the Besov energy. LP norm plus the Besov energy. So now I have my Newton-Sobolev functions in my domain. I have my Besov functions on my boundary. I can now talk about, oh no, I need one more thing to talk about boundary value problems, because I need to be able to talk about traces and extensions. How do I talk about traces and extensions at this level of generality? We know if you have a domain, even just in Rn, there's no guarantee that you have trace and extension operators, right? It depends on the geometry of the domain. So we have to talk about what are called uniform domains. If I have a locally, yes.
For less equality, is it the same term at left and right? The norm of in the same space.
Say it again, sorry?
Yes, is it the same term?
Is that the same term? So on the left here, this is B theta PP. On the right, this is the LP norm of F plus the HB theta PP norm, which is what I defined up above here, this Besov energy.
Okay, I see. Okay, sorry.
Yeah, so there's a H here,
HB,
and there's no H there.
Yes, okay.
Thank you for pointing that out. So now let's talk about uniform domains. If I have a locally compact non-complete metric space, I can call it a uniform domain if every 2 points can be connected by a very nice curve. Now, what do I want this very nice curve to do? I want the length of my curve to be comparable to the distance between the two endpoints. Right? This is sometimes called quasi-convexity. This means I can't have 2 points that are really close together, but the curve necessitates traveling very far to reach the other one. This eliminates, for instance, the slit disk. Right? The slit disk is a domain on which you can't correctly do, in my opinion, traces and extensions, right? And it's because if you take a point above the slit and a point below the slit, to join them, you have to join them by a very long curve compared to their distance. You also want the second condition is if I take any point along the trajectory of this curve that joins x and y, I want the length to either of the endpoints to not be too long in comparison to the distance to the boundary. This means my curve has to avoid going too close to my boundary. This is going to eliminate things like onions, because if you have an onion shape with a cusp, then points that are in the cusp by virtue of the concavity or convexity or whatever, the curvature of the cusp, any curve that goes to a point in the tip of the onion is going to have to get really, really close to the boundary before reaching the point itself. And so those are not points at which we call, those are not uniform domains if I have a kind of cusp like the onion domain. And why do I care about uniform domains? Because uniform domains are domains that allow for essentially non-tangential access to the boundary, because I can always approach the boundary by a sequence of points that are getting really close, because the boundary is the completion minus the set itself. So the boundary is exactly the limits of Cauchy sequences, right? So I can approach, and then each point that I'm approaching to, I can always join back to something by a uniform curve, and so I can get to the boundary. And that's how I define things like traces and extensions, is by using these paths that allow me to connect the interior of my domain to the boundary. So now what's the setting that I'm now going to bring everything all together? I have some p that's strictly between 1 and infinity. I have a metric measure space. My measure is doubling. It supports a p-Poincar inequality for the same p as above. I'm going to assume that omega is a bounded uniform domain. And I'm going to assume that the boundary supports a Borel regular measure that is theta codimensional for theta between 0 and p. So in particular, if you were in the smooth case of a 1 codimensional boundary, then you could choose any p that you'd like, because p is strictly bigger than 1. In this setting, I should point out that the measure nu is going to charge the boundary with a finite total charge. Okay. In this setting, the homogeneous versus inhomogeneous analogs of the Besov and Dirichlet Besov and Sobolev spaces don't care so much about if you have the LP part or not, because I'm bounded, but they do care about whether you're adding constants or not, if you're considering functions or functions plus C. So in this setting, let's now talk about what is known. What is known is that I do have a trace and extension operator. In particular, they're bounded linear trace and extension operators. This is a result due to Lucas-Mali. And even more so, the control of the trace and energy and the trace of the control on the trace and extensions are just in terms of the energies, not the LP. They're not going to actually play a role in the inequalities. So if I start off with a D1P function, so that's a function that has LP P weak upper gradient, then its trace is going to be in the Besov space. So it's going to have finite Besov energy. And the Besov energy is controlled by a constant times the energy of my function u. And the other way for the extension, the energy of the extension, the Sobolev energy, is controlled by a constant times the Besov energy. So I don't have LP anywhere.
Ryan,
yes.
Could you show again what the hypothesis on the measure on the boundary is? Yes, okay.
So this is in the if your alpha is regular, right? So if your balls have measure radius to the power of something, then defining dimension and codimension is trivial, right? Because it's just the power and the radius. But if you're dealing with doubling measures, this is the way to define codimension as opposed to dimension. So the nu, the way it charges balls, is like mu divided by r to a power. And that's why it's codimension as opposed to dimension. So now that I have trace and extension operators, I now can talk about boundary value problems, right? So very quickly, what's the Dirichlet problem for the p-Laplacian? If I start off with a Besov function on the boundary, then I say that a Newton-Sobolev function is a solution if it's a minimizer to the Dirichlet p energy over all Sobolev functions that have the correct trace. And now that I know what the trace is, I know what this gradient is, this is all well defined. You could do this in the setting of upper gradients as well, but this Cheeger differential structure gives you something more. It gives you an Euler-Lagrange equivalence, right? So you can say that the minimizer to this functional J is equivalently a solution to this Euler-Lagrange equation, where now I'm taking the inner product of the gradient of my solution with the gradient of an N1P function that has trace 0, right? So this is analogous to how we do it in the Euclidean case. This, for bounded omega, is solved. It's very classical. I don't even know where exactly to find it. It's just a matter of, since I have the trace and extension, you can run the direct method of calculus of variation. Okay, so this is Dirichlet. Now what about Neumann? If I have a Neumann problem, let's first do take one. My take one is if I have H that's an LP prime with integral 0 on the boundary, then I can define the Neumann solution with to the Neumann problem for the p-Laplacian as the minimizer of this functional, whereas the Dirichlet p energy minus the action of H on the trace of U. So this is the integral. I'm integrating the trace of my Sobolev function on the boundary against H. So this is because I don't in this setting have a notion of outer normal derivative, but this is a kind of weak outer normal derivative. And notice that nothing here cares about the addition of a constant. If I replace U with U plus C, the Cheeger gradient is linear. Upper gradients are not linear, which is another reason why they're a problem. Cheeger gradients are linear, and the Cheeger gradient of a constant is 0. The trace is a linear extension operator. Therefore, the trace of U plus C is the trace of U plus C. I know I said the same thing twice, but I think you know what I mean. And the fact that H is integral 0 kills that constant. And you're saying, okay, this is a perfectly fine Neumann problem for the p-Laplacian, right? Okay, great. And in fact, I can then even do an Euler-Lagrange formulation. And now the left-hand side is the same thing that I have for Dirichlet, but now instead of being equal to 0, it's equal to the action of this H on my trace. This is fine, but my problem is I was interested in the Dirichlet-to-Neumann map. In this formulation, I don't know how to start off with a Besov function on my boundary. I can p-harmonically extend it inside. I can solve the Dirichlet problem. But I then don't know how to come up with a Neumann boundary data that fits this regime. I don't have normal outer derivatives. I don't really know how to make it work. Now, this, of course, might just be my stupidity, right? Someone else might be saying, Ryan, it's very clear, do this, 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 this. But I don't know how to define the Dirichlet-Neumann map using this version of Neumann. So what I was thinking, well, I'm used to sometimes thinking about Neumann boundary data as being a function. But in fact, I'm never saying that U is equal to a function or the trace of U is equal to a function. I'm measuring the action of integration against this boundary value. So in fact, this is just an operator, right? This is just a bounded linear operator. And so I'm going to define the Neumann problem, but now my boundary data is going to be bounded linear functionals on the homogeneous Besov space. So in the previous example, the operation was integration against H. But of course, I could have other operators in this setting. So if I have a functional, a bounded linear functional on the Besov space on the boundary, I can then talk about the Neumann problem with this boundary data L as minimizing. Now it's the P energy, but now I'm going to subtract, instead of integration against this function H, the application of L to the trace of my Newton-Sobolev function. So this L of trace of U plays the role of the integral of trace U times H. And then in this setting, you again get an Euler-Lagrange equation, where now the left-hand side is what you would expect, and the right-hand side is the application of L to the trace of V, where V is any Newton-Sobolev function. And again, this formulation doesn't care about adding constants, because the fact that L is the dual of a homogeneous space means that L gives value 0 to constants. And since it's linear by virtue of being a linear, bounded linear functional, if I replace U plus C, then I get the L of the trace of U plus L of the trace of C. Trace of a constant is itself. L of the constant is 0. So nothing here cares about the addition of constants. Now, this was an Neumann problem that I could not find solved anywhere. The original one that I put with H being an LP prime, I couldn't tell you exactly where to find it, but it could be solved. Since omega is bounded, it's very straightforward. It's the standard kind of thing, right? You just kind of run the calculus of variations machinery. This setting I couldn't find. So I'm not going to go through the solution because I want to get to the Dirichlet-to-Neumann map, but the two kind of key estimates that you do, again, very classical. I want to show that my functional I is bounded. It's clearly non-positive because I can take constant functions. And then I can bound it below. And now what's interesting is the dependence, right? So I'm interested in what do all these estimates depend on. This lower bound of the Neumann energy functional depends obviously on the norm of L, right? Because that's the boundary data. And now it's an operator, so it depends on its norm. And the trace, because again, we're applying the L to the trace of function. So it depends also on the norm of the trace. Okay. And then how do you proceed? Now that you know that you have a bounded I, you can take an infimizing sequence, and then you get that this is actually another place where you need omega to be bounded. You can show that the energy of this infimizing sequence, or the sequence of energies of this infimizing sequence, is controlled from above now by the norm of your operator times the norm of the trace operator. Once you have now norm boundedness, you have a weakly convergent subsequence, and you can use reflexivity of these Banach spaces. Again, you can pass between the homogeneous and non-homogeneous, and you could by going to integral zero representatives and things. But you have reflexivity, you have completeness. You can use Mazur's lemma. You can upgrade from weakly convergent subsequences to convex combinations that converge strongly. And then you can show that the limit of this weakly convergent subsequence is going to actually be the infimum for I. So there will be a solution to the Neumann problem. So that's not so interesting, right? You can kind of imagine how that would go. But now I want to talk about what is the Dirichlet-to-Neumann map in my mind. Okay, so I want to relate Dirichlet boundary value problems to Neumann boundary value. I might be thinking about this all wrong, but this is the way I'm looking at it. So the Dirichlet-to-Neumann map, okay, I want to take homogeneous Besov functions on my boundary. That would be my Dirichlet boundary data. And now I need to relate to that boundary function an operator on the dual to then have a Neumann boundary value problem. And I'm going to show you how I do that. And interestingly, the norm of this Dirichlet-to-Neumann map is just in terms of the extension operator's norm, not the trace norm. This is going to come up later, right? Some things depend on the extension operator and some things on the trace operator. Maybe obvious to other people, but very interesting to me. So Dirichlet-to-Neumann, the control is going to be in terms of the extension operator. And how do I do that? I prove the following theorem. If I start off with a Besov function on the boundary that has Dirichlet solution, then I'm going to literally define so if f is my boundary value on the Dirichlet side, I'm going to literally define a bounded linear operator L sub f on the Besov functions and show that my Dirichlet solution is a Neumann solution for that choice of operator. So how do I do that? Well, I'm going to do the first thing that came to my mind is I'm wanting to pass through this Euler-Lagrange formulation, because that's really the strength of this Cheeger differential structure, that I have equalities, right? Because in the upper gradient world that I'm used to, right, how do you do PDEs? You don't have a P, a D, or an E, right? It's just minimizing energies. But this gradient structure allows me to actually get equalities in a weak sense, but nonetheless equalities. So the functional I'm going to define for my fixed boundary, Dirichlet boundary data, it acts on G by this integral that you remember from the Euler-Lagrange formulation. But now it was the inner product of the gradient of the solution with the gradient of V. My V is going to be the extension of the input into my operator, right? Because every a G in the Besov space can be extended to a V in the Newton-Sobolev space, and then I can take the gradient on that thing and use it in this function. So it's not difficult to see that this is a linear function. The integrals are linear, inner products are linear. The Cheeger derivative is linear. The only nonlinear thing is its absolute value, but the absolute value doesn't involve G, so it doesn't affect anything. So it's a linear functional. It's also well defined. You have to be a little bit careful because there's some subtleties. What if I change the representative of G? Is this going to change anything? And no, it won't. What if I change my extension operator? I claim the existence of an extension operator. Who's to say that's the only one, right? Again, this is not sensitive to choice of extension operator. That's not a problem. So now what we have to show is that LF is actually bounded, right? Because that's the whole point, is we want it to be a bounded operator to be a Neumann boundary value problem. And this is just some straightforward inequalities. The first step is just Cauchy-Schwarz. I put the absolute values inside my integral. Then I do what is, in my opinion, the obvious thing. You apply Hölder's inequality, right? Hölder then lets you get the LP norm of the gradient of the extension of G, and then the LP norm of the gradient of the solution to some power, right? Because this is not just the product of two functions. I have a power, so the power is going to kind of affect one of these LP integrals. And then in the next step, I'm going to use the fact that the extension operator is bounded. And remember, I said it was bounded in terms of energies. So this LP norm of the gradient of E of G is the Sobolev energy of the extension. That is controlled by a constant times the Besov energy of the function G. And now I'm going to use the fact that my U sub F was assumed to be the solution to the Dirichlet problem, which means it's a minimizer for the Dirichlet P energy. So the gradient of my solution U is controlled by the gradient of the extension of F, because obviously the extension of F is going to have the same trace F, because the trace of the extension is F. And then I can, by P harmonicity, control it, and then now apply the extension bound again. And so now I get the power of P minus 1 comes from one piece, power of 1 comes from the other piece. I get the norm of the extension operator to the power of P. And that is the piece that affects the norm of the Dirichlet-to-Neumann map, is this extension operator to the power of P. So now the only thing that I guess remains to show is that now this Dirichlet solution is in fact a Neumann solution for my choice of, now we have found properly posed Neumann problem. And this just means by the Euler-Lagrange formulation, I have to show that if I apply my operator L to the trace of V, that's the left-hand side of this equality, it has to equal the Euler-Lagrange piece. But this is actually immediate from the fact that my U sub F is P harmonic. It solves the Dirichlet problem. And this is a funny thing to write, but the trace of the extension of the trace of V is the same as the trace of V. That means that the extension of the trace of V has the same trace as V. So the difference extension of the trace of v minus v is a Newton-Sobolev function with trace 0. And so I can plug into the Dirichlet-Lagrange and then just use linearity of the gradient gives me exactly the first equality that I needed. Right? So it's all a little bit weird and kind of funky, but it works out. Now that I have Dirichlet-to-Neumann, I'm interested in Neumann to Dirichlet. So Neumann to Dirichlet, I'm starting off with a boundary value, an operator on the Besov space on the boundary, and I want to relate to that a Dirichlet boundary condition. That's not so difficult, but what's interesting now is the control of the norm of this operator is no longer in terms of the extension, it's in terms of the trace. I mean, maybe that just makes sense because now I'm going to Dirichlet, so I'm going to a trace thing. So it's affected by the trace. But it should also, in some sense, I would imagine, be influenced by the extension. So it's interesting that one is just in terms of the extension norm, the other one's just in terms of the trace norm. And so the theorem that you need is if you start off with an L on the boundary, a boundary linear operator, that's your Neumann data, and you have UL is the Neumann solution, then UL is actually a solution to the Dirichlet problem given by the trace of UL. That turns out to be rather easy to do because UL has exactly traced UL. What is interesting is now I want to get the control over the norm of the Neumann to Dirichlet map. And so that is in terms of the Besov energy of the trace of UL, but the trace is a boundary linear operator in terms of energies. So the Besov energy is controlled by a constant times the Sobolev energy of my solution. And now remember, when I solved the Neumann problem, I had control over the energies of my minimizing sequence, of my infimizing, or turned out to be minimizing sequence for my functional I. So again, you can do a kind of Mazur's trick to show that that same control on the energies of your infimizing sequence translates to control on the energy of the solution. And the energy on the solution was in terms of the operator norm of L and the trace, because I was defining I in terms of L of trace of U. And so if you rearrange it, you get this, and this is exactly where the trace power pops up. So if we put this all together, in fact, you can do a little bit more. You can show that the DTN and NTD maps are inverses of one another. And you have control of the Dirichlet-to-Neumann operator norm in terms of an upper bound using the extensions and a lower bound using the trace. Is this useful? I don't know. Is this interesting? To me, but that's because I'm not in this area. So to me, this is really interesting that I'm able to do so much, right? So some people get put off by the level of generality of metric spaces, but I think it's phenomenal that I'm able to do this much. If I have a few more, maybe one more minute, some further directions. What happens when omega is unbounded? What I did was really dependent on omega being bounded. The Dirichlet problem, as posed here, has been solved if omega is unbounded by published work of mine and ongoing work with Luca Capogna, Rika Corte, and Nageswari Shanmugalingam. It turned out to be a little bit technical and difficult how to pass from bounded to unbounded spaces. And it turns out to depend on whether your boundary is bounded or not. Not sure why, but it does. Then what about this dual? I can, of course, write down an abstract formulation for the dual, but what functions are in this dual, what functions are not in this dual? I would really like to get a better grasp of what it means. Because, for instance, in the Neumann problem, you can solve it for bounded omega with a function LP prime. The moment your omega is unbounded, LP prime is not enough. You have to have some control at infinity. So is that somehow reflected in this dual space? I don't know. And then, of course, the question is there a Steklov problem to be studied? And is there a Steklov problem that people would be interested in my studying? Or is this far too general and abstract once we bring it back down to concrete cases? I don't know. But there we go. Merci beaucoup tout le monde. Thank you for listening.
Thanks a lot, Ryan, for the talk. We have time for some questions. So if you have some, please unmute yourself and ask them right now for Ryan.
Perhaps I can start, Alex here. So, do you have example of these spaces that are actually more general than just to have some examples?
So you can look at obviously Riemannian manifolds that have non-negative, bounded Ricci curvature and things like this. People look at Carnot groups, the Heisenberg group, these kind of Carnot-Cartier-Dori groups and things like this. There are Laxo spaces, Benzler manifolds, very general domains, right? Even in the Euclidean case, some people just make everything Lipschitz, right? But you can do this on very general domains. For instance, the interior of the von Koch snowflake is a uniform domain. It's a hideous boundary, right? But it is a uniform domain, so you can do a lot of things there. But this is where maybe there's some negative aspects to my interest, is I'm not so much interested in doing the applications. I like this level of generality, and hopefully someone else can say, oh, now I can use it in my setting.
Thank you. Alexander, do we have other questions?
May I ask a question? So you said that when you talk about the extension and then you define your operator, you said that there is a extension, but we may have more than one, and it's independent of which extension we pick.
Yeah.
Is it easy to see, or
the fact that it's independent?
Yeah.
Comes from the fact that in this case, I'm assuming that my UF is harmonic. And so if I go to the Dirichlet version of Euler-Lagrange, if I put something in the spot of the energy that has trace 0, I get 0.
Oh, okay, so you use the uniqueness. Okay.
Yeah, any extension will have the correct trace to be an extension. And so you're going to end up getting it from just the fact that your UF is p harmonic. So this extension, for instance, is probably not the harmonic extension, right? I'm used to the Euclidean world, where it's obvious you take a convolution with the Poisson kernel and you get the extension as the natural one. Here, if you look at the way we define these extension operators, it's really not obvious. And it's not obvious that it's in any way optimal.
So when you go to the unbounded setting, then this is another obstacle, because then it may depend on the extension.
So so I do have in the unbounded setting with Nageswari Shanmugalingam, we have the existence of trace and extension operators, but certainly to do all of this in the unbounded setting, there are lots of kind of technical obstacles that it's not clear how to proceed, to be honest.
Okay, thank you.
Right. Thank you, Asma, for the question. So I was wondering myself, so in the Euclidean setting, there's a clear relationship between traces being well defined and the trace operator being bounded and the existence of extensions operators as well. Is it also this also the case in this metric measure space setting?
No. So the technicalities behind the existence of trace and the existence of extension are slightly different.
Okay.
In particular, there are some cases where you have extensions but not traces.
Okay.
And it's based off of this condition that Alexandre asked me to show. So here I have complete codimensional comparability. You could ask, what if the theta is different on the bottom and the top? What if I have a lower codimensionality and an upper codimensionality, or one and not the other? So one of the extension or trace, I think the extension only requires actually one of those directions. The trace requires both. And so there are some times where, for instance, there are domains where maybe you can't extend everywhere, but you can extend in a lot of spots. And then it wouldn't make sense to have a trace, because then you would probably be able to bootstrap and get more extensions. So take the onion, right? If you have the onion domain, except for that tip, the thing is a perfectly smooth domain, right? It's convex bounded domain. It's certainly uniform. It's beautiful. Yeah. So if you decide to just ignore that tip, you can extend it. You can, trace it around or something. or maybe I said it the wrong way. I meant you can take traces to most of the boundary and you can't extend. Sorry.
Yeah.
I said it the wrong way.
All right. And I had a second question. So is there any sort of representation theorem for the dual of these Besov spaces? Because for example, in the Sobolev setting, it's very natural if you're looking for Laplacians associated with a measure to see that when you define them by a quadratic form, the image of something in W1P should end up being in W1Q, where Q is the Erldow dual. Is there a similar kind of
None
relation?
that I know of. None that I know of. I really don't have a good grasp of what this dual is, right?
Okay.
Because so HB theta PP in the Euclidean world is WSP, where S is 1 minus theta over P. And then we define the dual. There are many ways to define the dual, right? You know, in terms of images under operators, in terms of Littlewood-Paley and atomic decompositions, in terms of triple-Lazorkin spaces. I don't know how any of those play out at this level of generality. And so I don't really understand this dual very well. Yeah.
Okay.
So that in itself is just an interesting thing, in my opinion, is especially if omega is unbounded and the boundary is unbounded. What is this space?
And I mean, I figure that when P is 2, right? Like this should at least have some sort of Hilbert space structure, right?
So this is interesting, right? In a lot of worlds, P equals to 2 is better, nicer. There's so much more, right? But for me, there's no difference between Laplace and p-Laplace because none of this has a Hilbert space flavor to it.
Okay.
In this abstract setting, the way to leverage p equal to 2 is to pass through probability, because probability also has an abstract metric measure space flavor, and they're really in love with p equal to 2.
Yeah.
And you can think about, you know, these things in terms of killing kernels and jump kernels and things like this. I don't have enough probability knowledge to make any headway for p equal to 2, but I would be interested in getting something for all p between 1 and infinity anyways.
All right. Do we have other questions for Ryan? All right, well, I guess we've exhausted the questions. Let's thank Ryan again for the talk, and we will resume next week with a talk by Severin Schraven from who will talk to us about two-sided lead theory bounds. So see you all around next week again. Thanks again, Ryan.